All right, we're ready to take a look at a sort of a different problem known as the Eigenvalue Problem. And this problem shows itself in different settings, and we'll hopefully, in the last lecture that we'll do in the course on Markov chains, show a specific application of the Eigenvalue Problem. But first of all, I just want to introduce you to the Eigenvalue Problem and talk about how to solve it. So we have a square matrix A that we're going to be dealing with, and we want to look at this equation here, right? AX equals, and this is the Greek letter lambda here, and lambda is a scalar value, and so we're looking at it in a statement that says that basically matrix multiplication is a scalar multiple, and we'll look at the geometric interpretation again of that as a refresher. But again, lambda is the variable that we use, the Greek letter lowercase lambda. So for some scalar lambda, and x, this vector x, right, which is n by 1, has to be non-zero. Well, let me rephrase that. We want it to be non-zero. Certainly if x were the zero vector, this equation would be true no matter what the value of A, the matrix A was, or the value of lambda. So that's not a very interesting case. But it gets interesting is when x is non-zero, and that's why we require that. So with this, lambda is called the eigenvalue of A, or the associated matrix operator T sub A. So again, we can think of this as a matrix transformation, or a matrix operator in this case, right, going from n space to n space, where the output is determined by multiplication by the standard matrix A. So eigenvalue, now eigen is coming from the German language. Basically it means unique value, unique or characteristic value, and so that's what we're looking for, this unique value that satisfies this equation, this scalar, what scalar will work for a given n by n matrix A. The vector x that's non-zero, remember, is called the eigenvector of A corresponding to lambda. So when we talk about geometric interpretation again, when we multiply by A, the net effect is a scalar multiple of the vector. So if the vector is vector x here, what are the geometric interpretations of scalar multiplication? What will AX essentially be? Well, if lambda is greater than 1, what's going to happen? That's simply a vertical stretch of that. It's a vertical stretch, a stretch, if you will, not necessarily vertical here, for lambda greater than 1. Okay, so because x is an n tuple, but if we were in 2 or 3 space, we can visualize it this way. But again, it's going to make the vector with a norm that is bigger. If lambda is between 0 and 1, what's going to happen? Well, it's going to shrink, right? If lambda is equal to 1, then of course we get just the same vector back, right? We get x back. And if what happens if lambda is less than 0? Well, then we're just going to be talking about same direction but opposite sense, right? And again, the magnitude or norm of this vector will depend on the value, again, of lambda. And then the last case is what? Lambda equals 0, which essentially is going to be the origin, if you will, just a point geometrically. And so when we talk about the eigenvalue problem, then geometrically we're talking about doing a matrix transformation that simply does this particular operation to the eigenvector. Okay, so how do we compute the eigenvalues? We're going to look at that first. How do we find these lambdas, as we're calling them, in this problem? And then we'll talk about how to find the eigenvectors. And again, later on in the last lecture, we'll look at a particular application of this. So how do we compute eigenvalues? So we start with our statement here, AX equals lambda x. And what I want to do here is I'm going to subtract, right, the matrix product AX from both sides. Remember, A is n by n, x is n by 1, so this is an n by 1. Any scalar multiple than n by 1 is n by 1. So I'm subtracting two n by 1 vectors. Okay. Now, what I want to do, you say, well, I want to factor out this x, and we're going to do a little adjustment here, because if you say, well, let's just factor that x out, it will have to be factored out towards the right here. But when I pull it out of these, what am I going to be left with? Lambda minus a. Does that make any sense? A scalar minus an n by n matrix? No, it doesn't make any sense. So before we do that, we're going to insert here the identity, right? The n by n identity matrix, right? So again, this is n by n. And still, this is n by 1, this is n by 1, right? Since I times x is just x. But now when I sort of quote-unquote factor out that x, I'm left with lambda I, which again is n by n, minus a, which is n by n. So I'm getting, it's making sense here. Well, it looks like a mess. N by n. Okay. Now, this manipulation gets us to this. And why go through all this stuff? Why am I going through all this stuff? Well, what we're trying to do is now find the solution to this matrix equation, right? Where lambda I minus a is an n by n matrix. Let's just call that B, right? Lambda I minus a is B. So I have a matrix equation bx equals 0. That's a homogeneous system, right? And we know such a system is always what? Consistent. There's always a solution, right? The trivial solution is always a solution. Again, if x is 0, that solves this equation. However, keep in mind that we are looking for what? Non-zero values of x that satisfy that. We don't want the trivial solution to this, nor to this as well. And so the question I have is, in order for there to be non-zero, non-trivial solutions to x, what must be true of the matrix lambda I minus a? Remember, we're calling that B up there. So if I have bx equals 0, then what must be true of the matrix B? Well, remember, B is n by n. So bx equals 0, first of all, has only the trivial solution if what? Bx equals 0 has only the trivial solution if what? If B is invertible. Remember that list of equivalent statements? But we don't want the trivial solution only. We want non-trivial solutions. So bx equals 0 has non-trivial solutions, then what? If and only if what? B is singular. So we want B to be the matrix B to be singular. Let's say we want that to happen, right? So how do we make the matrix B singular? Well, that list of statements, right? Bx equals 0 has non-trivial solutions now, right? All those lists of equivalent statements to B being invertible, each one of those are now false. So of all those statements, and remember the last video, we looked at the whole long list, right, in the book, right? Chapter 4, section 10 at the end. I would encourage you to make sure you look at that long list and begin to remember all those equivalent statements. But the easy one that we're going to use here is what? That this matrix lambda I minus a is singular if and only if what? Its determinant is equal to 0. Right? If it was invertible, then the determinant would be what? Not equal to 0. Okay? So when we take the determinant of lambda I minus a, what we're going to get is a polynomial. It's going to actually be a degree n polynomial in the variable lambda, and that's what we call the characteristic polynomial. Setting that characteristic polynomial equal to 0 is called the characteristic equation. Remember the eigenvalue problem, eigen meaning unique or characteristic value. And so this is where we get the words characteristic for the polynomial and characteristic for the equation. So let's just go right into it and look at an example of finding eigenvalues for a matrix. So again, we're interested in solving the equation, right? Lambda I minus a x equals 0. We're looking for non-trivial solutions, and so we want this matrix to be singular. Well, let's see what that matrix is. And I'll do all the steps here the first time. get? We get, of course, here I do the scalar multiplication. I get lambda 0, 0, lambda, right? This is lambda. This is the identity matrix here. 2 by 2, of course, right? Because we're dealing with a 2 by 2 matrix A. And then I can do the subtraction very easily. And what do I get? I get lambda minus 1 in the first row, first column entry. 0 minus a negative 8, so be careful. 0 minus a negative 8 is positive 8. 0 minus a negative 4, positive 4. Lambda minus a negative 3 is lambda plus 3. Okay. A very common mistake is actually done, students all the time will do this. They'll say 0 minus a negative 8 is negative 8. They'll just, for some reason, they don't see the minus there. Or they'll say 0 minus a negative 4 is negative 4. So that will cause problems later on if you're not careful with that. So just be careful with the simple arithmetic there. And now what are we saying? This matrix we want it to be singular. Therefore, its determinant must be 0. Let's go ahead and find the determinant, though. How do I find the determinant of a 2 by 2 matrix? It's AD minus BC, right? So this product minus this product. So it's lambda minus 1 times lambda plus 3 minus 8 times 4. And let's go ahead and expand and combine like terms. If I FOIL this out, I get lambda squared. Outer is 3 lambda. Inner is negative lambda. 3 minus 1 is plus 2 lambda. Negative 1 times 3 is negative 3. 8 times 4. And then I can combine negative 3 and negative 32. Okay. That right there is what we call the characteristic polynomial. And we're interested in what? Making this matrix again here singular, and therefore its determinant must be 0. So if I equate the determinant that I just found, and which is, notice, a degree 2 polynomial in the variable lambda, by setting e equal to 0, this is what is referred to as the characteristic equation. Okay. And now we want to solve that equation. Well, again, solving a quadratic equation should be no problem. If you can factor it, that's the way you should proceed. Otherwise, you can use the quadratic formula. This does factor fairly easily, right? And so what do we know? Lambda is equal to negative 7 or positive 5. So there are the eigenvalues. These are the eigenvalues, and there's 2 of them. These are the eigenvalues. Okay. And as double check, I mean, if you wanted to check that you did this right, you can plug in these values for lambda back into this matrix here. And like if I plug in, say, 5, I'm going to get 4 here and 8 here. And if you think about it, 4, 8, 4, 8, is that matrix singular? Is its determinant 0? Yes, it is, and it should be. And so these 2 values of lambda are the only values such that this matrice's determinant is 0. Okay. Just a little word before we go on. When we're solving these characteristic equations, then what can happen if I can't factor it? I can use the quadratic formula. Well, we know when we have a quadratic equation, the possibilities are I can have 2 distinct real zeros, like I do here. Or I can have 1 repeated 0, like if it factored as, say, lambda minus 5 quantity squared, then I would just have 1 eigenvalue. Or you can actually have eigenvalues that are non-real complex conjugates, right? So like you might get 3 plus or minus 2i. And so it is possible to have eigenvalues that are not real numbers. Now, when we talk about eigenvectors, we will generally avoid finding eigenvectors in problems where the eigenvalues are not real. Okay, let's look at another example. This was a 2 by 2 case. Let's look at a 3 by 3 case. As is true in general, when we step up to bigger size matrices, it gets a little more complicated. the process is still the same. Of course, now our characteristic equation is going to be a degree 3 polynomial. So what I like to do is I like to go right to finding the determinant of lambda I minus a. And I'm going to do all this in my head, so to speak. And so, you know, in the last problem, I wrote it out step by step. I would encourage you to do that if you're having troubles, because this causes problems. So lambda I minus a. So remember, this has lambda down the main diagonal, zeros everywhere else, and then the a is here. So I have lambda minus 0, which is lambda. I have 0 minus 0, which is 0. And then 0 minus a negative 2. 0 minus a negative 2 is positive 2. It's very important. I see so many students will say that's negative 2 there. You're subtracting, and it's 0 in the first row, third column for this matrix, and negative 2 for this matrix. And so 0 minus a negative 2 is plus 2. So please watch your arithmetic. 0 minus 1 is negative 1. Lambda, right, middle entry here is the second row, second column entry is lambda. Lambda minus 2. 0 minus 1. 0 minus 1. 0 minus 0. Lambda minus 3. Right. So there is the determinant we need to find. So how are we going to do this determinant? Well, I'm going to do cofactor expansion. And what row or column am I going to do cofactor expansion along? Well, if you didn't say the second column, then you're in trouble. We're going to do second column because there's 2 zeros in the second column. That's what you're going to do, cofactor expansion along column 2. Don't make this more difficult than it has to be. And so what do we get here? I get 0, right, times its cofactor, plus lambda minus 2 times its cofactor. So what is it? It's negative 1, second row, second column, to the 2 plus 2, which is going to be negative 1 to the fourth, which is positive 1, times its minor. How do I find that minor? I take out the column and row that entry is in, and I collapse it down, and I get my minor, so the corner entries. Plus what? 0 times its cofactor. Okay. So now, of course, this is positive 1. I get lambda minus 2. And what's the determinant here? Well, the determinant here is, right, AD minus BC. So it's lambda times lambda minus 3 minus 2 times a negative 1. Of course, that's negative 2. And if I clean this up, lambda times lambda, lambda squared, lambda minus 3 lambda, minus a negative 2 plus 2. Okay. Oops. Sorry. Okay. I mean, this is the characteristic polynomial. Now, if you want it, you could expand this all the way out by multiplying these two, doing all those multiplications and combining like terms. But I like the factored form better because that's going to tell me right away what the eigenvalues are, right? The zeros, really, of this polynomial. And so I would encourage you in the process to begin factoring as soon as possible. Don't really expand this back out because then it'll be too hard to factor it, potentially. So just begin factoring now. Now again, if you look your answers in the back of the book, they might have the might want you to give the characteristic polynomial, and it may be an expanded form. But I'm going to go ahead and factor this right here, right? And how does this factor? Lambda minus 3 lambda plus 2. Well, factors what? Their product is 2. Sum is negative 3. It's negative 2 and negative 1, right? And I can write this a little more compactly because these two factors are the same. This is lambda minus 2 squared times lambda minus 1, right? So this is the characteristic polynomial. The characteristic equation is setting it equal to 0, and therefore the eigenvalues are the solutions to the characteristic equation, which are going to obviously be lambda equal 1 and lambda equal 2. So there are the eigenvalues. Now notice I've got two eigenvalues here. I can have up to as many as 3 distinct eigenvalues in this case because it's a third degree. If you expand all this out, it's a third degree polynomial in lambda. And but we only have 2, and the reason is 2 is a 0 of multiplicity 2, right? The factor lambda minus 2 occurs twice. Okay. So you can have, for a degree 3 polynomial, and therefore for a 3 by 3 matrix, you can have 1, 2, or 3 eigenvalues, distinct eigenvalues. All right, we did a 2 by 2, 3 by 3. Let's now look at a 4 by 4. Now, certainly gets harder, and you've got a degree 4 polynomial, but this one I made it so that's going to be a little bit easier. So the 4 by 4 matrix now with lambdas down the main diagonal, zeros everywhere else. So I have lambda minus 3, 0 minus 0, 0 minus 0, 0 minus 0. Second row, I got 0 minus 1, lambda minus 2, 0 minus 0, 0 minus 0. 0 minus 4, 0 minus a negative 1, be careful, positive 1, lambda minus a negative 3, lambda minus a negative 3, lambda plus 3, 0 minus 0. 0 minus 5, 0 minus 0, 0 minus 2, lambda minus 1. Again, if you're having trouble constructing these, I would just go ahead and write out lambda I and then subtract a. Make sure you're clear on how to get all this. Now, notice our lambda I minus a is also lower triangular. And we know something, though, about the determinant of any triangular matrix. What is the determinant of any triangular matrix? Remember, it's the product of the main diagonal entries. So for this particular case, there's my determinant. Now you can certainly expand that all the way out, be my guest, but that is the characteristic polynomial. If you expand it all the way out, it's a degree 4 polynomial in the variable lambda. But we're interested in the eigenvalues. Do we have the eigenvalues? Yeah. Lambda is what? Negative 3 or positive 3, 2, and 1. So it's plus or minus 3, 2, and 1. There's 4 distinct eigenvalues. Now, going back to the original matrix, right? We've got the eigenvalues down here, negative 3, 2, and 1. Negative 3, positive 3, 2, and 1. What do you realize about those eigenvalues in the original matrix? Well, I hope you recognize that what? They are simply these entries along the main diagonal. Is that always true for any lower triangular matrix? Will the eigenvalues always be these main diagonal entries? Is that always the case? Well, if you think about this process, your answer should be yes. And in fact, it's true for any, not just lower triangular, but upper triangular or diagonal, any triangular matrix, all right, which includes upper, lower, or diagonal. They have their eigenvalues located along the main diagonal. So it has to be triangular. In general, any matrix that's not triangular, that is not necessarily true. Okay. All right, so what we're going to do, now that we've talked about how to find the eigenvalues, those aren't too bad. You can certainly run into some rather challenging polynomials, especially if you're talking about a 4 by 4 or higher. Degree 4 and higher polynomials can be very tricky in general to solve. Factoring them is not always easy, and so that's a big challenge. That's more of a computational thing. So if you're a computer science person, there are some problems where you're finding eigenvalues for very large matrices. That process is more challenging and sometimes different than what we're doing, more of a numerical method approach. I will say this about eigenvalues. There is something called the most dominant eigenvalue, and that is a problem that is applied every time you search on Google, and Google lists all your results from your search in order. How does it know which search to go first and second and third and so on? Well, there's an algorithm for that, the Pagerank algorithm. and that algorithm involves actually the process of finding this most dominant eigenvalue. But they're dealing with matrices that are 100 by 100 or more. Okay, so we'll stop here with this video, and we'll go on in the next video and look at how do we find the corresponding eigenvectors. That's a little bit more interesting problem, a little more challenging in some ways, and we'll do that in the next video.